Today I have another video for you, and today we're going to be discussing EGMO 2016 Problem 6. Before I jumped into me trying to solve this question, which I'll be attempting to do right now, thank you for all the support. Just a little announcement about the videos. So I'll be trying to aim around one video per week. The reason is because I have a life, and you should get one too. And I can't post that often. Next video will probably be geometry, as we already passed a lot of number theory recently. And I still remember about the video on author problems that I promised to make. I'll do that as well, so that'll be sorted out. Okay, I won't take any further of your attention span because it's pretty much low. It's usually like 3 minutes if I look at statistics. So I'll try to do the best I can in the short time we have together. So let's start with a question. We have a set being a set of positive integers n such that n to the power 4 has a divisor in the range n squared plus 1 to n squared plus 2, and then we need to prove that there are infinitely many elements of S of each of the form 7m, 7m plus 1, 7m plus 2, 7m plus 5, blah, 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 and none of the form 7m plus 3 and 7m plus 4, where m is an integer. So we have this n to the power 4 thing. So let's just start. So board is doing some weird things. Okay. Yeah, so we have this kind of weird thing that n to the power 4 is divisible by n squared plus k, where k is in the range of 1 and 2n. So obviously this is not the condition that I'll be trying to work with, but eventually we want to make some statements mod 7 about n. So that's just the thing to keep in mind, that we are still, at the end, we'll be looking at mod 7 at some point. But right now, the condition that n to the power 4 is divisible by n squared plus k is the only reasonable condition we can work with. And this bound here essentially will be useful when we will try to bound n squared plus k. Wow. But the thing that I want to start with is just Euclid's algorithm. So n to the power 4 is divided by n squared plus k, and we know that n to the power 4 minus k squared is divisible by n squared plus k, because this is a difference of squares of n squared and k. So therefore we get that k squared is divisible by n squared plus k. And this is useful because essentially, because of this bound, we know that since 1 is less than or equal to k is less than or equal to 2n, we can bound k squared as less than or equal to 4n squared. And the reason why we kind of do that, like always when you have k being bounded from the top, usually what comes to my mind is to get k on the other side, so get to this side of the inequality and try to bound it from the top and use that in order to limit some stuff. And in this case, we get that since k squared over n squared plus k must be a positive integer, so it must be a positive integer. Sorry for the z. Okay, let's just redo it because that just angers me. Okay, z plus. We know that this fraction, which is a positive integer, it should be less than 4n squared over n squared plus k, which is less than 4n squared over n squared, which is 4. So essentially this means that this fraction, if we call it a, we know that a is equal to 1, 2, or 3, one of those three, which is already a pretty good thing we got so far. So yeah, now I think it's just casework, so let's start with equals 1. So if a equals 1, then we get k squared is equal to n squared plus k, where k is again the range of 1 and 2n. Is this even possible? I mean, probably not. Uh, let's just think why. Yeah, it's not possible because k squared minus k should be a perfect square. Yeah, it's bounded between k minus 1 squared and being less than k times k minus 1 and being greater k squared. Well, the opposite way around. And see, since k minus 1 squared and k squared are consecutive squares, there's no other square between them, so a equals 1 case is impossible. Okay, now let's move on to case number 2. So case number 2 is a equals 2. So now we have k squared be equal to 2 times n squared plus k. And if we transfer 2k to this side, we actually can get that k times k minus 1 squared will probably be better, will be equal to 2n squared plus 1, which is a thing called Pell's equation. So Pell's equation is an equation of shape x squared minus dy squared equals plus or minus 1. Usually 1 is the standard thing. Minus 1 is also a good case. There are some free cases with like y to the power of 4 and the right hand side being 4, and then you have like one or two solution, which is like the Ljungren's theorem or something like that. And there are cases with 5 where it applies to Fibonacci numbers. But that's not what we are interested in. We're interested in this thing, in this equation where x and y are positive integers. And this is called a Pell's equation, essentially. Um, and yeah, if you still didn't know this, we do have one here. Minus 2n squared equals 1. And essentially, if this is true, if such k exists that k minus 1 squared minus 2n squared equals 1, then obviously k will be in the range between 1 and 2n. So we may just look at solving this thing and showing that so yeah, essentially we want to, first of all, if we remember, like always try to remember what we are trying to get to, and what we're trying to get to is to mod 7 about n. So I assume right now we can, that's like the perfect moment to use this, and we want to show that n can't be 3 or 4 mod 7. So let's assume we're trying to solve this, and let's assume n is congruent to 3 or 4 mod 7. And on the side, let's just write down all the remainders that x squared can give mod 7. The usual way to do is you draw a table like this. This is pretty bad, but you draw the remainders of x. 5. Okay, guys, just don't make any 6, 7 jokes. I'm actually gonna be pretty mad. Okay. So yeah, x squared will be 0, 1, then 4, then 2, and 2, 4, 1. That's our remainders mod 7. So 2n squared in case of this will be congruent to 4 mod 7. And therefore x squared must be congruent to 2n squared plus 1, which is congruent, well, it's equal to 2n squared plus 1, which is congruent to 2 mod 7, I think. Wait, that's a bit weird. 3 squared is 2, so yeah, that's a bit depressing. Let's think. So we want x squared minus 2n squared equals 1. So wait, none of the form, no elements of S have the form 7n plus 3 or 7n plus 4. So yeah, I mean, just kind of awkward. So if n is 3 or 4, let's just check the table again. 0, 1, 4, minus 2, 1, 7. Okay, 3 or 4 is obviously 2 mod 7 and 2n squared is 4. Oh yeah. Oh my days. I made a stupid arithmetic mistake. Yeah. So if 2n squared is 4 mod 7, then the whole thing is 5 mod 7, which is impossible. Yeah, sorry guys. Um, which is like no solutions. So, by the way, the fun thing that I learned is like no solutions is the same. It came from phi, from the Greek letter phi, which is kind of crazy to me. Um, but yeah, that's side note. Okay, so in this case, we showed that solutions of 3 or 4 mod 7 are possible. And the other thing from Pell's equation that we actually know is that it has infinitely many solutions. And so if we look at x squared minus 2n squared equals 1, we can generate infinitely many solutions by looking at one solution x0, y0, or n0 in this case. And then essentially what we do is we look at uh, so yeah, let me teach you all the theory if you don't know it yet. If you know it, you can revise it or just skip this part. So essentially, if we look at this equation, Pell's equation, what it claims is that if there exists a solution, x0, y0, which is a solution, essentially what we claim is that if we take a number this, which is like I think is a fundamental unit, is the correct term, and we look at this number here, and we raise it to a power of k, and get something like xk plus yk root of d, then xk yk is a solution, and moreover, if the norm of x0 plus y0 square root of d, which is I think x0 squared plus y0 squared is equal to 1, uh, then xk, yk is generating all the solutions, something like that. Maybe I'm mistaken about this part with norm, but if you get a solution, if you get one solution x0, y0, then xk, yk is a solution always. And this is the main fact you usually use in Pell's. And just as to when you use it, is usually Pell's is used when you want to show that there are infinitely many solutions, or you want to generate infinitely many solutions, or stuff like that. So it doesn't like you can sometimes use that it's all solutions, but it's much rare. So in this case, uh, the simple solution to this that I see is 3 and 2. So 9 minus 8. So here we can take the fundamental unit of this and write it down as xk plus yk root of 2, and say that xk, yk is a solution. And if you remember, we want to show that there are now infinitely many solutions that are like every other modulo except for 7. Oh, mod 7 except for 3 and 4. So the way we actually do this is we probably want to look at xk, yk, but you can generally like write it off. But what we can do instead is try to write it down recurrently. So if I look at xk plus 1 plus yk plus 1 square root of 2, it will be equal to xk plus yk root of 2 times 3 plus 2 square root of 2. So from here, we actually get the xk plus 1 by the like RIP lemma, which is just a fancy way of saying that the coefficient here will be like next to square root of 2 will be the same as the coefficient next to square root of 2 here, and the one that's just an integer will be the same as the integer. So xk plus 1 will be equal to 3xk, plus 4yk, and yk plus 1 will be equal to, so coefficient next to square root of 2, yk, so it's going to be 3yk plus 2xk. So now let's look at this thing mod 7, starting from the pair 3, 2. So from 3, 2, we go into pair, so xk plus 1 will be, okay, first of all, let's just keep it nice and tidy, and rewrite this as 2xk plus 3yk. Okay, so now 3, 2 will go into 9 plus 8, which is 17. So xk plus 1 will be 17, which is 3, I assume, not 7. And yk will be equal to 2 times 3, which is 6, and 2 times 2, which is 6 again. Wait, yeah, 3 times 2, yeah, so it's 12, which is 5 mod 7. And remember, we are looking at what n gives, so it's essentially what y gives mod 7. We're looking at yk mod 7. And yeah, so we go into pair 3 and 5, from where we go to pair what? 3 times 3 plus 4 times 5, which is 29, which is 1 mod 7. And 3 times 2 is 6. 5 times 3 is 15, so the sum is 21, which gives us 0. And from 1, 0, we go into 3, 2. And we loop up from here. So essentially, we showed that yk infinitely many times achieves residues 2, residue 0, and residue 5 mod 7. So we showed that in this case, there are no solutions that are 3 or 4 mod 7, and there are infinitely many solutions that 2 or 0 or 5 mod 7. So yeah, but if you didn't forget, we still have the case where a equals 3. So if my memory doesn't work incorrectly, then it was something like this, is equal to 3. So k squared is equal to 3n squared plus 3k. And again, a very important note is that if k is a solution to this, k is also less than 2n, so we don't have to worry about like sorting out stuff about what do we call it? Sorting stuff with inequalities. If we get a solution, it already works to the initial one. But it's important note to do. So here we see that everything is divisible by 3. So k is divisible by 3. So let's write k as 3 times t. So we get 9t squared equals 3n squared plus 9t, which essentially yields 3t squared equals n squared plus 3t. Let's say that's not what we want. That's not what we want yet. Yeah, so we want now to say that n is equal to 3 and 1. Or let's call it 3, 3s for Sidorenko. And then we get that 3t squared is equal to 9s squared. So either we're going to get like something like infinite drop downs of dividing by 3, or we'll get something else. So in this case, we'll get 3t, and then we get t squared equals 3s squared plus t. So yeah, I think we are stopping at this moment, and I think what we have to do is say 4t squared minus 4t plus 1 equals 12s squared plus 1. And this is a Pell equation, so we get 2t minus 1 squared minus 12s squared equals 1. And since this has to be odd in in any case, if 2t minus 1 was like, if I want to essentially do a substitution x squared minus 12s squared, the reason why I can do that is because as x is odd, as if it was even, then 1 would be even, which is a contradiction, obviously. So I just want to solve this, which is another Pell's equation. First, what we want to do is check mod 7, that if n was congruent to 3 or 4 mod 7, then there are no solutions. So let's assume n was 3 mod 7. This yields that s was... Okay, so n is essentially plus minus 3 mod 7, which leaves us s to be plus minus 1 mod 7, which leaves 12s squared to be congruent to 5 mod 7. And so x squared is congruent to 12s squared plus 1, which is congruent to 6 mod 7, which means that x squared is congruent to minus 1 mod 7, which is impossible because the table residue didn't have one, or minus 1 over 7 should be a quadratic residue, minus 1 mod 7. But minus 1 to the power of 7 is minus 1 to the power of 7 minus 1 over 2, which is minus 1, contradiction. So we've shown that 3 and 4 can't be the values of n mod 7. And now we probably need to do the same trick. So first of all, we need to, again, use the Pell's equation with t equals 12. But it's a bit trickier because, I mean, Pell's important notes, when we try to generate all solutions, D has to be square free. In this case, D is not square free, but we just want to generate infinitely many solutions, so that won't bother us. So for example, we just need to find one solution, and then, which is, yeah, I found it. So 7 and 2 will be a solution, because 49 minus 48 equals 1, so it's a solution. But now we have to look at 7 plus 2 squared of 12, which is essentially 4 squared of 3. So if I look at this thing squared, it'll be equal to 49 plus 48, which is 97, I think, and plus 56 squared of 3. And 97 squared minus 12 times 56 squared, I think is 1. I mean, you can check it manually. I'm a bit lazy to do that, but okay, let me just pull up my calculator and check it real quick, but just for your notice. That's how dedicated I am to proving my point. But yeah, I mean, okay, 97 times 97, right? 97. 9409. Okay, if I told you something wrong right now, I'll be shameful, but oops. So 12 times 56 and times 56. 37362. Okay, what did I do wrong? 1 second. So what did I do wrong? Okay, 7 plus 2 square root of 12, which is 7 plus 4 square root of 3. 48, 49, 97. And then, oh, oh my god, oh my days. Okay, 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 yeah, yeah, yeah. It's not 56 squared. Okay. Oh my god, I lost so much more. Okay, yeah, so 7 plus 4 square root of 3 is not exactly what we want, because what we want was 7 plus 2 square root of 12. And we are looking at everything that has root 12 and not root 3. So if we look at this squared, the coefficient next to root 12 is 28. Okay, and we get 28 squared. And now, yeah, now it should be fine. So 97 times 97 is 9409, and 12 times 28 times 28 is 9400. So that works. Okay. Yeah, so essentially, the main point of what I was trying to prove and show to you guys is that you can always generate infinitely many solutions. In terms of is it all solutions, it's not always true, but you, if it's square free, then yes. But you also need to take the fundamental unit with more equals one. Okay, so these are the solutions. So now we can do the same trick. So with x0 equals 7 and y0 equals 2. Oh, then we want to define everything recurrently again. So xk plus 1 plus yk plus 1 is xk, oh, wait, root 12 is equal to xk plus yk root 12 and times 7 plus 2 root 12. So this thing leaves us xk plus 1 to be 7xk plus 24 yk, and yk plus 1 leaves us to be 2xk plus 7yk, something like that. Yeah. And since we are looking at everything mod 7, this is congruent to 3yk mod 7, and this is congruent to 2xk mod 7. So essentially, since we started from 0, 2, because 7 is 0, we go on to 6 and then 0, from where we go to 0 and 5. Wait, yeah, 5, from where we go to 1 and 0, from where we go to 0 and 2, and then we loop up. So now we get that there are infinitely many solutions where yk plus 1, yeah, yk plus 1 was congruent to 2, 0, 5 mod 7. And since they're congruent to 2, 0, and 5 mod 7, then we know that it was, well, yk plus 1 was essentially s. So that's s. So 3s, which is the same as n equals 3s, is congruent to 6, 0, and 15, which is 1 mod 7, and there are infinitely many solutions of that. So we cover infinitely many solutions that are 6, 0, or 1 mod 7, and we also cover infinitely many solutions which are 2, 0, 5, which is 1, 2, 5, 6, 0. And that's what we wanted to show. And we also showed that there are solutions that are 7m plus 3, well, 7m plus 3 or 7m plus 4, which is equivalent to like 3 or 4 mod 7. So yeah, I think this is a pretty instructive problem that involved like pretty cool ideas. So if you have to take away something from this question, I hope you took away something new about Pell's equation. If you didn't, then that's absolutely fine, because that means that you already know this, and that's very, very good. For those of you who don't know this, I hope this was like useful and entertaining because of my amazing charismatic personality. So yeah, thank you everyone for joining in, and I'll try to upload a video next week. See you guys.